Okay, so we'll go ahead and get started here. This is where we left off yesterday with this problem. There's not enough room to do this on the PowerPoint, so I'm going to do this on Smart Notebook. But this is yesterday's notes, so we're just going to finish this up quickly. Maybe quickly. This is kind of a long, involved problem, but it will help us with what we're doing today as well, so it's important that we cover it. So here's the problem, and this is basically what I was talking about, where now we're mixing a bunch of stuff together. So it's not just one thing in the solution. We're putting a weak acid, a weak base in there, and then we're going to add a strong base to it at some point. Okay, so this is not that bad. You just need to remember, we talked about this rule at the very end yesterday. Stoichiometry first, equilibrium second. Okay, and what that means is, now that doesn't apply necessarily to the, well, no, it does, because we're adding the base even in part A. So, yeah, so this is going to apply from the very beginning. When you're adding a strong base into a buffer solution like this, and just a reminder on what a buffer solution is, that's when you have a weak acid, and usually it's conjugate base in the solution in close to the same concentrations because it resists pH change when you add a strong base or a strong acid. Okay, so that's the usefulness of it. So if we want to know the pH of a solution after we add some NaOH, this is kind of a tricky problem, right? Because we've got 0.3 moles of the acetic acid and 0.3 moles of the sodium acetate in the solution. And then we want to know what's the pH of the solution after 0.020 moles of sodium hydroxide is added. Okay. Now, kind of important to note here, we're given our values in moles. Okay. And the reason for that, that's actually kind of nice, because when we do stoichiometry, we want to do it in terms of moles, right? When we do ice tables and equilibrium and stuff like that, we usually are thinking in terms of concentration. But when we're doing stoichiometry, we want to be thinking about moles, okay? So this is a 1 liter solution, so it's not that difficult to change it to molarity anyway when we need to. But for right now, the fact that we have moles is actually kind of helpful. Makes it a little bit easier, okay? So let's just think about this for a second. We've got a acetic acid right here, that's a weak acid, and we've got sodium acetate, that's going to dissociate and end up being a weak base, right? Does everybody see that? Because the sodium's not going to do anything in the solution, but the C2H3O2 1 minus is going to end up being basic, okay? It's the conjugate base for acetic acid. When we put sodium hydroxide into that solution, what is it going to react with? It's going to react with the acid, right? Okay. Bases react with acids. So we've got the sodium hydroxide here. The OH minus here is going to react with the acetic acid, right? So, excuse me. So the stoichiometry we've got to think about here is the reaction of the sodium hydroxide with the acetic acid. Okay, so let me come over here and show this to you on here. Sodium hydroxide, as soon as I put it into water, what's it going to do? It's going to dissociate, all right? So then we end up with OH minus, which is kind of the thing that we care about. The sodium doesn't do anything in the solution, okay? And we're worried about the reaction of the hydroxide with the acetic acid, okay? Now that doesn't mean that the acetate is not in the solution. It is, okay? But we're not too worried about it right now, okay? We will be in a minute. So when these two things react, what's going to happen? Right, this OH minus is going to pull the H off of the acid, or the acid is going to donate it, however you want to look at that, and it's going to make H2O and C2H3O2 minus. Okay, now I have drawn a forward arrow only here, okay? That's because this OH minus is a strong base, okay? That's going to completely react with the weak acid until the OH minus is completely gone, okay? So So that's why we draw a forward arrow on this. For strong acid, strong base reaction, we draw forward arrows. For weak acid and weak base reactions in water, we draw equilibrium arrows. Okay. Now, there is going to be an equilibrium here after the OH minus is completely reacted, so we'll talk about that in a minute. But that's what I mean. We pay attention to the stoichiometry first, and then we think about our equilibrium after that. Okay. Now, how much OH minus do we have in this solution, or are we adding to the solution? 0.020 moles. Okay. Actually, I started this too far over. I'm going to do something a little bit different here. Okay. When I do the stoichiometry, I'm going to think more about just initial versus final conditions. Okay, we don't have to do an ice table here, so this will be if. Okay, now you have if tables, I guess. I don't know. Initial conditions versus final conditions. This is a little more useful when we're thinking about stoichiometry, I think. And I actually may teach stoichiometry this way next year at the beginning of the year because I kind of like it. But what we have here initially is 0.020 moles of the OH minus, right? Now, how many moles of the acetic acid do we have initially? 0.3. Is it 0.300? Are there two sig figs there? Or two zeros? Okay. Now, we also initially have some acetate in that solution, right? How much acetate do we have? Isn't it also 0.3? I'm not looking at it right now, but I think they're the same. You guys see that? Because the sodium acetate, there are 0.3 moles of that. So when that dissociates, you end up with 0.3 moles of the acetate ion. Okay. So those are our initial conditions. All right. Now, with stoichiometry, all we're thinking about here, this is all 1 to 1 to 1, right? So basically, if we have 0.020 moles of the OH minus, that's going to react with how much of the acetic acid? All of it. Or, well, no, I mean all of the OH minus is going to react, right? Okay, so basically it's going to react with 0.020 moles of the acetic acid. Does that make sense? Okay, so ultimately this is going to be gone. Okay, how much of this are we going to have left? I guess you could do a change. I mean, you almost could do an ice table here also. It's kind of the same thing, but you're going to have 0.280. Okay, and then how much of the acetate are we going to have? No. Right, because 0.02 of this is reacting with 0.02 of the acetic acid. Okay, so what we're going to end up with here is 0.320. Does that make sense? And I actually, you know what? This actually does make sense to do an ice table with, so maybe that would be easier instead of introducing if tables. Maybe we can do ICE here. Okay, because think about this. This is going down by 0.020, right? So that means this is also going down by 0.020, so that gives us the 0.280. And because this is on the other side, it's going up by 0.020, okay? Maybe that makes more sense. Let's just do ice tables, okay? So that's telling us our new concentrations here, okay? Now, that's important because now we've got to think about equilibrium, okay? So all we did by adding this OH minus is we changed our concentration of our acid and conjugate base a little bit. Does everybody see that? Okay, so now these are our new concentrations of our acid and conjugate base. Now, thinking back from yesterday, how do we calculate the pH of a solution when we have a significant concentration of an acid and its conjugate base? You guys remember the name of the formula? Something Hasselhoff. Yeah, the Henderson-Hasselbalch equation, right? Okay, so then we've got, so again, this is stoichiometry first, okay? And then we think about equilibrium second. Usually with the equilibrium, you can just use Henderson-Hasselbalch. Not always, okay? If all of this acetic acid gets used up, then we're going to have to just use a regular ice table to figure this out. But since there's still a significant concentration of both of these, we can just use Henderson-Hasselbalch. So pH equals pKa. Did I give you the Ka in this problem for the acetic acid? What is it? 1.8 times 10 to the negative fifth. Now to get the pKa, we have to take the negative log of that. And now I can't locate my calculator. Oh, it's in the back. Thank you. Does anybody have the negative log of that? Actually, I think it's 4.74, isn't it? Okay, do you know how I figured that out without, or how I could have figured that out even if I didn't know it? Let's take a look at the problem for a second, okay? It tells us the pH of the buffer is 4.74, right? Now remember, we had equal concentrations initially of the acid and its conjugate base, so when that happens, pH equals pKa, right? All right, so our pKa here would be 4.74 because that's the pH of the initial buffer solution. All right, so 4.74 plus the log of the base over the acid concentration. Now, we're talking concentration here, but the nice thing about this problem is we're in 1 liter of solution, so they're the same, okay? So 0.320 divided by the concentration of the acid, which is 0.280, okay? So once we work that out, and again, the order I do this in, just because I don't trust my calculator, is I divide the 0.32 by the 0.28, and then I take the log of that, and then I add that to the 4.74, which gives me 4.80, I guess, for my new pH. Is that right? I mean, we just added a bunch of OH minus into that solution, and the pH went up by 0.06. That's because the buffer solution is working, right? Okay? The buffer solution resists those changes in pH. Now, the second part of the problem I like because it says for comparison, let's see if we added 0.020 moles to 1 liter of pure water. Then how would that change the pH? Okay, so now if we come back over here and just think about this for a second, how do you find the pH of a strong base? A long time since we've done this, I guess. Just negative log of the concentration, that's going to give you the pOH, right? And then if you subtract that from 14, that'll give you the pH, okay? So if we take the negative log of, well, what's the concentration here? It's still 0.02, right? Because it's in 1 liter of solution. So 0.02. So if I take the negative log of that, that gives me 1.70 basically. That's my pOH, okay? So then my pH of this solution would be 12.30. I should have been able to do that in my head. Now look at that. That is a big difference, right? So you put that much OH minus into pure water, you raise the pH to 12.3. You put it in the buffer solution, it's still 4.80. Okay? So that's a big difference. That's why we use buffer solutions. They actually really work as far as resisting those changes in pH. Okay, let's look at the next one and see if we need to go over that one. It might be very similar. The only difference on this one is that you have to be careful with your volume measurements, and they will do this to you sometimes on the AP exam, where they give you, okay, we're adding 50 milliliters of this with 50 milliliters of this, and then we dump in 50 milliliters of this, okay? So the thing you have to watch out for there is that changes your volume, which also changes what? Your concentration, okay? So you just have to be, that's one kind of extra thing that you have to watch out for on these. So what we're doing in this one is we are mixing the propionic acid, I'm not sure how you pronounce it, with the sodium propionate, and they want to know the pH of that solution. Okay, so the first part of this, you're actually just calculating the pH of the buffer solution. Okay, and then they're saying, what if you add 50 more milliliters of HCl? Actually, I think this one would be useful to go over because it's a little bit different. So let's take a look at this. So part A here is just asking, what's the pH of the buffer solution? Okay, and they're giving me a Kb, so it kind of makes sense to me to write this equation in terms of the base reaction, because I think then we don't have to really. Oh, you know what? Yeah, I was trying to shortcut, but we're gonna have to, if we plug this into Henderson-Hasselbalch, we're gonna have to get the Ka anyway. So yeah, you're right. We should probably do the acid. Um, okay, so let's see here. We've got 50 milliliters of the 0.1 molar solution and 50 milliliters of a 0.1 molar solution. Okay, so first thing we have to watch out for here is that we're going to change our concentrations. But this first part is fairly easy, because if we double the volume, what does that do to our concentrations? It halves them, right? Okay, it cuts them in half. So that, we don't really have to worry too much about calculations. You don't have to do an M1 V1 equals M2 V2 on that one, because it's fairly straightforward. We might have to in a minute with the HCl. So HC3H5O2. Okay, when that weak acid reacts with water, it's going to make H plus C3H5O2 minus. Okay? And so when we do that reaction, you can make an ice table for this one, or you can just plug this into Henderson-Hasselbalch. I would probably prefer to plug it into Henderson-Hasselbalch or Hasselhoff. Okay. So finding the pH of this solution, we need the pKa, all right, which they gave us the Kb on this one. The Kb is 7.69 times 10 to the negative 10th. So if we just divide that by, or divide 1 times 10 to the negative 14th by that, that'll give us the Ka. Divided by 7.69 tenth. It's going to give us 1.3 times 10 to the negative 5th. Okay, and then if I take the negative log of that, so I can get the pKa instead, it's going to be 4.89 plus the log of the base concentration over the acid concentration. But do I really need to do this? They're equal, right? So if we have 0.05 over 0.05, that part cancels out. Our pH is 4.89 initially. Okay. So yeah, that's kind of nice and easy when they're equal. Okay, all you have to do is find the pKa, and then you've got your pH. So there's that. Okay. Now for part B, what if we add 50 milliliters of 0.1 molar hydrochloric acid to the mix? Okay. So now we have to be a little bit careful. We need to do some stoichiometry on this, right? Okay. So if we add HCl into this mixture, what is the HCl going to react with? Going to react with the base, right? And the base is going to be the C3H5O2 minus. All right. So our relevant reaction here, we're going to have H plus C3H5O2 minus. And what is that going to do? It's going to go to completion, and we're going to make some of the propionic acid. How do you say that? Okay, so then if we make our normal ice table here for our stoichiometry, this is where it gets a little bit tricky. How many moles? Remember, we want to do this in moles when we're talking about stoichiometry, okay? So that's the one thing I guess I don't like about using an ice table here is I've programmed you guys to use molarities in your ice table, and now I'm telling you, well, when you're doing these reactions that go to completion, you want to use moles in your ice tables, okay? As long as you can keep that straight, then ice tables are fine for this, I think. So, how many moles of H plus do we have here? You guys remember how to figure that out? You remember molarity equals moles over liters, right? So if you have your volume and you have your concentration, if you multiply those two together, that will give you the number of moles. But the thing you have to watch out for is this volume has to be in liters. Okay, so 0.05 is going to be your volume in liters times 0.1 would be 0.005. Okay, so we have 0.005 moles of the H plus. how many moles of the C3H5O2 minus do we have? 0.005. And how many moles of the propionic acid do we have initially? No, actually we have some in there because it's a buffer solution, right? So initially we have the same amount. So basically what we're doing is we're adding the same amount of all of these into this solution. Okay, now this is a very common problem that you might see on the AP exam. Okay, so what's going to happen here? Remember, the H plus reacts until it's all gone or until the base that it's reacting with is all gone, right? Okay, so this goes down by 0.005, so does this, and this goes up by 0.005. Right? So at the end, we have none of the H plus, but we also have none of the conjugate base, right? We just turned it all into propionic acid. So this is going to be 0.010 now. That's the number of moles of that we have. Okay? And what is the question asking? I forget. What is the final concentration of propionic acid? Okay. Now here's where we have to be a little bit careful. We just figured out the number of moles that we have, right? It's 0.010. How many liters of solution do we have here? 0.15. We just added 50 plus 50 plus 50. That gives us 150 milliliters, which is 0.15 liters, right? So to figure out the concentration, we need to take the 0.010 divided by 0.15. Okay, when you do that, you should get 0.067, I guess, for the molarity. Okay, so that's our concentration of the acid at the end. Now another question they could ask us that would be harder on this one. They could ask us what's the pH of this new solution. Any ideas there? Well, no, you can't do that. You can't negative log the acid concentration because this is a weak acid, right? So this isn't going to completely dissociate. So what happens here, it's kind of a two-stage process, right? That's why we think stoichiometry first, equilibrium second. This is going to go to completion so that we have none of the H plus or of the weak base. Now all of a sudden, all we have in that solution is a weak acid. And now it's just like we did in the last unit, where we're starting with a 0.067 molar concentration of a weak acid. We make an ice table, figure out what the pH of that solution would be. Because immediately, as soon as this reacts, you can kind of think of it as a two-stage thing, this is going to start being in equilibrium with the water. Does that make sense? Okay, now it's not asking us that question, but if it was, that's what we would do. Okay? So then, is the final solution an effective buffer? What do you think? Why not? Why is it not an effective buffer? Yeah, there's now no conjugate base in that solution, right? It would do an okay job at buffering if we put a strong base in, but it's not going to buffer at all if we put in a strong acid, okay? So this is not an effective buffer anymore. So at some point you can add enough strong base or strong acid to, render the buffer ineffective. Does that make sense? Okay, moving on. Acid-base titration notes. We're going to get as far as we can on this today, and then we're going to do part 2 of this tomorrow. So titration. You guys should be familiar with the titration. Now, you don't have any blanks to fill in here, so I'm going to go pretty fast through this. You have example problems and graphs to write and stuff like that, but we know what a titration is. We've already done one of those this year. You guys remember that, where you use the burette to add the base into the acid, and it changes pink when you're close to the equivalence point. Now we added a strong acid to a strong base. That's the only kind of titration that we have done so far. Okay, so when you add a strong acid to a strong base, what is your approximate pH at the equivalence point? When you neutralize the acid with the base, it should be right at 7, right? Okay. Now that's not the case when you add a weak acid to a strong base or a strong acid to a weak base. Okay, it's going to be a little bit different. The equivalence point is just the point where you have an equal number of moles of acid and base in the solution at the same time. Okay, and then the titration curve, you also graphed that, so hopefully you remember what those kind of look like. If you don't, we're going to graph a bunch of those today. So yeah, ooh, like that. There you go. Actually, it kind of goes, like that. You'll see it. Maybe I should just show you the picture. Okay. 4 main stages to a titration, and actually everything we just did with buffer solutions is going to help us out with this. Okay. So we're going to have an initial pH, and there are a couple different ways to figure that out depending on whether we're talking about a strong acid or a weak acid initially in our solution. Then we've got the stage that's between the initial pH and the equivalence point. So we've started adding the base. Usually a base is added to acid, not always. Okay, but that's the example we're going to work with today. But there's going to be a time between when we start adding base, but we haven't reached the equivalence point yet. Okay, and then there's a stage in the titration where we're at the equivalence point, and then after the equivalence point. Those are kind of the 4 stages that we need to talk about. Each of those stages has its own calculation that goes along with it, which is fun. So this is a typical titration, and this is the strong acid, strong base titration. Okay, so you have a place on your notes where you can write this graph down. You don't have to write down all the details here. Okay, the main thing I want you to get is the shape of the graph, and I want you to notice a couple of things here. First of all, the beginning pH is very low. You guys see that? With a strong acid, the beginning pH is going to be very low. Okay? Now notice another thing. See where the equivalence point falls here? It's right at a pH of 7. Okay? And then the other thing I want you to notice is this curve right here is incredibly steep. Right here, okay? And so that's the way it's going to work on a strong acid, strong base. There's not going to be a lot of change in pH for quite a while because you've got a lot of H plus in that solution, but the OH minus is reacting with the H plus, it's reacting with the H plus, and then once we get right about here, now there's no more H plus in that solution anymore. It's all been used up. I mean, really, technically, once we get here, that's when exactly all of the H plus has been used up. But when it gets pretty close to that equivalence point, all of a sudden you have this drastic rise in pH, because now there's no H plus in the solution to react with the OH minus anymore. And now the pH is just determined by the amount of, you're just dumping OH minus into that water now. Okay? Does that make sense? Okay, so that's a strong acid, strong base titration. So stage 1, this is actually a pretty easy calculation, and we've done this quite a bit before. Okay? All you have to do is look at the initial concentration of the strong acid, and you can figure out the pH. So how do we figure out the pH of a solution if it's 0.1 molar hydrochloric acid? See, now there's too many things to remember now. See, that's the hard part with these. All the different techniques we have. Negative log, okay? It's as simple as that, because this is a strong acid. It's going to completely dissociate, right? So 0.1 molar HCl is the same thing as 0.1 molar H plus, right? And if we know our concentration of H plus, then we can figure out our pH fairly easily. You just take the negative log of that. Anybody want to take a stab at what the negative log of 0.1 is? In other words, negative log of 1 times 10 to the negative 1. Does that help? You remember that? If you have 1 times 10 to the negative 1, you take the negative log of that, the pH is going to be 1. Yeah, you look at the exponent, right? Okay, so pH is equal to 1. Okay. Stage 2 is between the initial pH and the equivalence point. Okay, so then the pH is going to be determined by the concentration of the acid that hasn't been neutralized yet. Okay, so we still have more H plus before we get to the equivalence point. We still have more H plus than we do OH minus. Okay, so the H plus concentration is still greater than the OH minus concentration at this point. So all we have to do is figure out how much H plus we still have in that solution. Take the negative log of it, and that'll give you your pH. Okay. And you would have to do a little stoichiometry with that. Okay, and we're going to do a couple examples on this, or at least one example, I guess. Okay, at the equivalence point, calculation is really easy. In fact, there is no calculation necessary for strong acid, strong base, because at the equivalence point, pH is 7, because now all the OH minus and the H plus have reacted and they've just formed water. So with a strong acid, strong base reaction, remember, you end up with water and you end up with some sort of salt. Okay? And that salt, for a strong acid, strong base reaction, neither of the ions in the salt are going to affect the pH of the solution. Okay? So, for example, in ACl, right? Na plus doesn't affect the pH of the solution, Cl minus doesn't affect the pH of the solution. Okay? So pH is going to be 7 for a strong acid, strong base titration. Then after the equivalence point, what you need to know is how much extra OH minus have we dumped into the solution, and you can use that to calculate your new pH. Okay? So fairly simple calculations when we're talking about strong acid, strong base titrations. Okay, here's a practice problem. Calculate the pH when the following quantities of 0.1 molar NaOH solution have been added to 50 milliliters of 0.1 molar HCl. So first of all, 49 milliliters, and then second of all, 51 milliliters. Okay. So for A here, what stage of the titration are we at? Think about the 4 stages we just talked about. This is going to be before the equivalence point, right? So what that means is, before the equivalence point, there's still a little bit more H plus in that solution than there is OH minus. We need to figure out how much H plus is left, and that'll help us to figure out the pH. Okay? So we need to do this in terms of moles, because the equivalence point is always in terms of moles. Okay? The equivalence point is when you have equal number of moles of the H plus and the OH minus in the solution. Okay? So how many moles of HCl do we have here initially? 0.1. Well, wait a second. No, sorry. That's the concentration initially. .05 times 0.1, right? Which would be 0.005. Okay, so let's think about the reaction that's happening here. The reaction we care about, the H plus and the OH minus are reacting to form H2O. Okay? So then again, we can kind of do an ice table here, but just remember this is a stoichiometry ice table, so we're using moles, not molarity. Okay? But you just told me the initial H plus concentration is 0.005 here. Is that right? I didn't put too many zeros there, did I? It's 0.05. Yeah, that's right. Okay. And then how many moles of OH minus do we have at this point? 0.0049. Does everybody see that? So this is very close to the equivalence point. I mean, very, very close. Okay. It's cold in here this morning. Okay. So, the H2O doesn't really matter here. I don't really care about that too much. We could talk about the number of moles of water that we have, but it's not significant because it doesn't matter for our pH. What we need to know is how much H plus and OH minus we have left at the end. Okay. So here, because these two are reacting, the H plus is going to go down by 0.0049, right? And the OH minus is going to go down by 0.0049. Does everybody see that? Does that make sense? Because these two are going to react. The OH minus here, this is essentially a limiting reactant problem at this point, right? Because the OH minus is going to run out first. So then what we end up with here is 0.0001. Did I do that right? And then 0, okay? So now our concentration, well, that's the number of moles of the HCl that we have, okay? Now to figure out the pH, we need the concentration of the H plus, okay? So we need to take 0.0001 moles divided by the number of liters of our solution. And that's where, again, you have to be careful, because we now have a solution that's more than 50 milliliters, right? Because we've added an additional 49 to it. So this is 99 milliliters, which would be 0.099, is that right? Liters. Oops. So I'm getting a concentration of basically 0.0010. Sig figs are we using here? I guess we're doing 3, so 0.00101. That's my concentration of H plus at this point. Okay. And if I take the negative log of that concentration, that gives me a pH of 2.996. Okay, so the pH has gone up a little bit, but still, even that close to the equivalence point, the pH is still pretty low, right? So we're getting really close to where it all of a sudden just jumps, okay? But we're not quite there yet. Does that make sense? So that's our A, okay? Now B is at 51 milliliters, okay? So now what we have to think about, we can still use the same equation here. So I'm just going to erase some of this stuff, keep my ice table. Okay, so now we have 51 milliliters of the OH minus. So this is going to be now 0.0051 moles, and we still had the same amount of H plus to begin with, 0.0050, right? Actually, I guess I should have an extra 0 on the back of each of those for sig figs. Okay, so now my limiting reactant is the H plus, right? I have a little more OH minus in the solution than H plus. So the H plus is all going to react now. I'm going to end up with none of this, and I'm going to end up with 0.00010 of the OH minus. Okay. Hopefully I'm doing my numbers right here. I'm trying not to use the calculator. So now I've got OH minus in the solution, extra OH minus. So now I need to take the negative log of that concentration. Okay. But then I have to remember that's a POH, so then I need to subtract that from 14 to find my pH. And then the other trick on this one is the volume's not quite the same as the last calculation we just did. It's close. But what's the volume now? 101 milliliters, so 0.101 liters, right? So then our concentration is going to be 9.901 times 10 to the negative fourth. Okay. If I take the negative log of that, that's going to give me a POH of 3.004. So then subtract that from 14. Gives me a pH of 10.996. It was 3.004. Okay. So again, just notice the drastic difference between 49 milliliters added and 51 milliliters added. The pH has jumped up from basically about 3 to about 11. Okay, and you guys have seen that when you've done the titrations. Oh, added 2 drops, and now it's completely pink, right? Okay, so that really does happen, and that's kind of why. All right. Okay. So because the pH change is so drastic at the equivalence point, really the indicator that we use, it's important, but there's a range that we can kind of use. I mean, if you go back to the graph here, notice, and then this is the example that it's giving, methyl red changes at about pH 5 to 6, okay? Phenolphthalein changes at pH, 8 to 9, 9 to 10, somewhere in that range. Either one of those indicators is acceptable for doing a strong acid, strong base titration like this. Because, I mean, honestly, there's almost no volume change there, between that pH change. So either one of those indicators is going to give you about the same value of the volume added for the base to get to the equivalence point. Okay. Now let's finish this. After the equivalence point, we just talked about this. Oh wait, we passed that? Yeah, we did the example. Okay. Titration of a strong base using a strong acid would be exactly the same, but backwards. Did I give you a space where you could write a graph for that? Okay. You don't have to write this down, but here's how it would look, okay? So if you got a strong base, where's the pH going to start? It's going to start high, right? So start up here. It's going to go down slowly, and then all of a sudden it's going to drop, okay? So you see how that works? Okay, it's just exactly the opposite of the other graph. Okay. Usually we titrate an acid with a base, so we add base to acid. That's typically the way that we do it, but you can do it this way sometimes. I mean, usually a titration is used when we don't know the concentration of an acid or a base. So if you don't know the concentration of the base, then you would have to add acid to it and see what happens, okay? All right. Trying to decide how far to go on this. How many pages do we have left on the notes at this point? Just front and back? Okay. One page front and back? Yeah. Okay, I think we can probably cover all of that tomorrow. So, and this is kind of a good stopping point, so we'll go ahead and wait for that, the next type of titration tomorrow, okay?